Hello everyone. In this lecture, we will be proving one theorem of chi-square distribution, which is very important in applications. And then we will move on with one application of chi-square distribution. So let me share my screen. I hope the screen will be visible to all of you. So this is the theorem that we are going to prove right now, and it's a very important formula we will be using in applications of chi-square distribution. So as all of you know, that S square is the random variable which represents sample variance. So the basic definition of S square, I will write it down over here. So S square basically is defined as summation xi minus x bar whole square divided by n minus 1. Now this definition differs just in the denominator with population variance, because in the definition of variance or population variance we have n, but in sample variance we have this term n minus 1. This is because we are trying to get the unbiased estimator of the population parameter sigma square. So what is meant by an unbiased estimator of the population parameter? So you know, sigma square is the population parameter, namely population variance, and its expected value should match with the corresponding sample variance parameter, namely S square. So if I take the expectation of this S square with this definition, then surely we will get the sample variance S square. So therefore, in the denominator of S square, we have this term n minus 1. So this is the basic definition of S square. So now, if this basic definition of S square we know, S square you can also write it in this form. Okay. So let us prove how we can arrive at this formula as given in the theorem. So let's start with the proof. So by definition of S square, with this definition I'm talking about, S square is 1 upon n minus 1 into summation xi minus x bar. X bar is a sample average whole square, where I will run from 0 to n. Okay. So now the same thing we can write as 1 upon n minus 1 into summation xi square minus 2xi x bar plus x bar square. So what we did, we have just expanded the square in the previous state. So this x square is expanded, xi minus x bar whole square is expanded in this form. So let's go ahead. So this we can write as 1 upon n minus 1 summation xi square. Now I will be attaching that sigma summation sign with all the terms that are dependent on I. X bar is independent of I. So index variable is I, and this x bar is independent of I. So we can write it outside the sigma summation sign. So that is 2x bar will take outside sigma summation sign, and then we will be having summation xi over there. Again, in the third term, x bar square is independent of I, so we'll write outside the sigma summation sign. I will run from 1 to n summation 1. So this is the last state. Now the same thing we can write as 1 upon n minus 1 summation xi square minus 2 summation xi divided by n. So what I'll do, I will write x bar as summation xi by n. So all of you know that x bar is the sample average, and we can write it as summation xi by n into summation xi as it is. Okay. And then you will be having summation xi whole square upon n square, as I'm writing x bar whole square into n. Okay. So I hope this last term is clear to all of you. So what last term is saying? Last term says that this x bar we can write as summation xi by n, other term as it is. X bar square we can write as summation xi square by n square into summation 1 contributes to n. So this is how the last thing goes. Let me complete the bracket. So this bracket is completed. Okay. So with this, we'll multiply now the numerator and denominator by n. So let us multiply and divide by n to the last step. I'll move to the next page. So we will give 1 upon n into n minus 1. Into bracket we have n times summation xi square minus 2 summation xi whole square plus summation xi whole square. So if I divide and multiply by n, so look at this step. Suppose I divide by n, then I should multiply by n, right? So first term becomes n times summation xi square. The second term becomes summation xi whole square, that is written over here with 2. And the last term will be having n square in the numerator, okay, and n in the denominator. So we will be having simply summation xi whole square. Now here, this is 2 times summation xi whole square, and here it will be having simply summation xi whole square. So minus 2 plus 1 will be 1. So I can write this next term as 1 upon n into n minus 1. Then you have n times summation xi whole square minus summation xi whole square. Okay, so and this is nothing but s square. So this formula is getting arrived as we want in the theorem.